Suppose that we have a constrained equality optimization problem, and we found candidate local point for optimality by solving the equation gradient of the Lagrangian equals 0. Okay, and x, where x star is a regular point. Then we have the following test we can make to check whether the candidate point is a local minimum or a local maximum. So let's see why such determinant is appearing. So let's see, have an idea then of the proof of the theorem. Okay, so just to clarify our idea, just the beginning of the hint of the proof. So if the only function that connects our function to the content is the Lagrangian. So we will use the Lagrangian for that. Okay, for the comparison using Taylor's, the same idea, Taylor's formula. Okay, we will apply it for the Lagrangian. So if we apply for the Lagrangian, so we will have x star plus h2, so lambda. Okay, L is a function of x and lambda, so we can write it's x star. As long as we have the right regularity on f and g, we can do that. Okay, plus the sum. So this is plus the gradient instead of writing the sum. So the gradient of L at x star, lambda, and h. Okay, the gradient in so yes, the gradient, because you have gradient of x, so Taylor's formula in x. Okay, in space x, because gradient, yes, for x only. Okay, in x, so it's not what I wrote here. Okay, so for the function as a function of x, so it will be the sum from I to 1 to n of L xi x star lambda hi, okay, plus half of the double sum, okay, Lxi xg x star plus ch and lambda hi hg for some c between 0 1. Okay, so I from 1 to n and g also from 1 to n. So this we can always write it. Now we use the fact that these quantities are 0. Okay, that are 0, and then we use the fact that we can always write L x star L lambda as f. So by the definition is f x star minus lambda 1 g 1 x star minus c1 etc. minus lambda m gm x star minus cm. But these are 0 because x star is because x star belongs to the set of the constants. Okay. Okay, so now subtracting the two, and yes, we can express differently L at x star plus h lambda. So using the definition of L, so it will be fx star plus h minus lambda 1 g1 at x star plus h minus c1 etc. Lambda m gm at x star plus h minus Cm. Then we subtract the two equalities, so we will get the difference here, fx star plus h minus fx star plus this sum, and here we eliminated this term. This one is fx star. So finally, we can move this sum to the other side and have this equality. So x star plus h minus fx star. Look at what the difference we have, because this is that will allow us to deduce the comparison. So it will be the sum of the lambda k of gk at x star plus h minus ck, okay, from N1 to m, okay, and plus half of the sum I and j from 1 to n, 1 to n h. So those are lxi, xj, the intermediate points ch and lambda, and hi and hg. You see, and then another step is to write this difference as, because this ck is exactly our g of gk at x star, so this difference we can write it also a sum. Let's write it in another color. So this sum of the partial derivative, okay, xg at an intermediate point plus ck h, okay, hg, and g from 1 to n. Okay, so we have this writing, and then this suggests so we need of course more steps to, but that's why we see that we have a quadratic form here that intervenes. So if we have this something that this quantity is positive under something here equals 0, okay, and then we can deduce a sign of this difference. Okay, so and there is a theorem in algebra that discuss positivity of quadratic forms, okay, under let's say contracts. Okay, so here is how it is formulated here. Let's put it here bigger, larger, so that you can see it well. Okay, so here it is. It says that if we have a quadratic form and okay, if we show that it is, because this is tangent plan, if we show that this quantity will be positive on the set of constants, here is you have g prime, almost g prime dot h, then you deduce the positivity of your quadratic form. Okay, so it is positive on the set for any h, then you can deduce that you have a strict local continuous minimum. Okay, so this is a hint of the proof of the theorem, so that you are not surprised why these big determinants are appearing. Okay, so it comes naturally. We use it the tools to extend the idea for the situational and constrained using comparison and Taylor's formula. Okay, so let's do an application and see an example how to apply the theorem. So the first example is the following. Look, the first example is, yes, find the local max of the function fxy equal xy over subject to the constant g xy equal x plus y equal 2 for x positive and y positive. So first let's sketch the set of the content. So it's simple one here. Okay, so for x equals 0 I have y equal 2. So here is the point of my content. For y equals 0, x equals 2. So it's a line passing through those 2 points. I am considering only the part x positive and y positive, so I'm restricted to these line segments. Okay, so my set is this one. Now we are our interest is finding local maximum, that is not the endpoint of the set. Okay, so we are looking for something here. So let's do that. Yes, so so what we want to do, apply the theorem. So we need to check regularity of the point, find the critical point of the Lagrangian. So let's introduce first the Lagrangian for this problem. Okay, so L of xy and lambda, there is one constant, so we will have m and m here is 1. Okay, so let's introduce Lx y lambda is equal to to fxy, which is xy minus lambda, one constant x plus y minus the c, which is 2 here. Okay, so the first step is found the critical points. My Lagrangian is differentiable, so I can look for the critical points. Okay, so gradient of so I need to solve dl dx, which is y minus lambda equals 0, dl dy, which is x minus lambda equals 0, and finally dl d lambda, which is minus x plus y minus 2 equals 0. So these two first equation gives x equal y equal lambda, which I can substitute here and get 2 lambda. So 2 lambda minus 2 equals 0. So this says that I have the only solution, x y lambda equal 1 1, and lambda will be 1 also. Okay, so the only candidate point is the point 1 1. Here it is in the graph here. Here it is, my point 1 1. It is an anterior point, so I would like to classify, but before that we know that the theory uses the fact that the point is a regular point, so we need to check the rank condition. So let's check the rank condition. So the rank condition, so we need g prime of x, y. It's the vector 1 and 1. So it's always different from the 0 vector. The first column is linearly independent. So the rank is 1. Okay, rank of g prime of xy is 1. It's equal to the m. So yes, any point on the content is, the set of content is regular. So 1 1 is a regular point. In particular, 1 1 is a regular point. Now the second, now classification. Let's deal with the classification of the points. Classification. So we need to estimate the BR. Okay, so here we have m, so n equal 2 and m equal 1, so we need to estimate only one b2. Okay, b2 we have, so r goes to from m plus 1, which is 2, okay, which is n also, so we stop. We have b2. b2 is formed as below, so at xy is equal. So let's look at the definition so that we can apply it. Okay, so we put the gradient of g, so 0 first, the determinant, then g prime, yes, 1 1, first derivative, the transpose here, and the Hessian of our Lxx. Okay, Lxx is 0, Lxy is 1, Lyx is 1, Lyy is 0. Okay, so this is the determinant we found, and if you do the calculation, it is 2. Okay, yes, so maybe to remind you how to compute this such determinant, so usually we can compute along the column or the line depending, so put the sign plus minus plus, so it will be 0, and you eliminate the row and the column, you are at the level this with plus, so 0 0 1 1 0, minus, then minus the coefficient here, you put it, and then you eliminate the row and the column, and you have then 1 1 1 0, and then plus 1 times the, yes, you eliminate the row and the column, and you get then 1 1 0 1. So like that you have 0 minus 1, so it's minus 1, this one is 0, and then here 1 plus 1, so it is so did I do a mistake here? Minus 1 times, yes, here it's minus 1 times minus 1, I did a mistake here, it's minus 1 times 0 0 minus 1, so it's minus 1, so it will be 2. Okay, so we have b2 positive for any xy, but in particular at 1 1 b2 is positive. What else? b2 is positive, r is 2. Okay, so we are here. Okay, the second test, yes, so it works. Yes, we have minus 1 r b2 1 1 equal minus 1 2 b2 1 1, okay, equal 2, which is positive. So yes, 1 1 is local maximum point relatively to the continent set. Okay, so this is how it works. Okay, so yes, we can do one more maybe. But this time I will not look for the point, so that we can go faster. So the second example is the following. Second example 2. So we are asked to find the local max also of the function. This time the function has 3 variables. Okay, so f, x, y, and z. It's xy plus yz plus xz. So subject to the content gxyz, which is x plus y plus z equal 3. So suppose that, so we introduce, of course, the Lagrangian Lxyz. So here m is 1, so be careful here, m is 1. Okay, so n is 3 variables, so I use just one Lagrangian multiplier. Okay, I will need only one. Okay, and so this will be my function xz minus lambda of the context plus y plus z minus 3. Okay, so let's write quickly the system for gradient L in x in the variables y, z, and lambda equals 0. So it's equivalent to Lx will be, so I will give you quickly y plus z minus lambda equals 0. Ly, we can write x plus z minus lambda equals 0, and Lz is y plus x minus lambda equals 0, and finally L lambda will be minus of x plus y plus z minus 3 equals 0. Okay, so we have our system. Now suppose, but I'll leave you that it's easy to solve. Suppose that we showed that we have the point x y z equal 1 1 1 with lambda equal 2. Okay, and we want to classify our point. So here also regularity, it's easy. G prime at any point x y z is the vector 1 1 1, so the rank condition is satisfied. G prime at 1 1 1 is equal 1, which is m. So regular points, we have a regular point. Okay, so we can continue like that. Now, okay, so let's continue here. Now we want the classification. So for classification here, we said R must make the test m plus 1 up to n. So that is m plus 1. M plus 1 will give me 2, and n is 3. So I need to consider, so we need to consider for r equal 2 and then r equal 3. For r equal 2, so we need to compute the determinant b2. Okay, b2 first at x, y, z. So what is b2? So that means, so yes, pay attention to the last line of the theorem. It says it suffices, no, not this one, the theorem, here it is. There is this, I didn't mention this. The variables are renumbered in order to make the first m columns in the matrix linearly independent. So suppose that when you compute your derivative g prime, and you found here 0, so the first column is linearly dependent, so you must change the order of your columns, that which induce the change of the order of variables. You see, so you need to do this exercise so that you get used to it. For our situation, we need the first, so we need the first, we said m. The m here, m is 1, so the first one is 1, is linearly independent. We don't need to change. Okay, so we need to put then the two first variable, so gx and gy. Okay, gx, gy, gx, gy, and lxx, lxy, lyx, and lyy, like that. Okay, which gives me then 0 1 1 1 1. And what about the other one and 1 here? Okay, lxx, then yes, we can deduce the second derivative is 0. Lx with y is 1, ly with x is 1, and lyy 0. Okay, and this value is exactly 2, and it is positive. Okay, great. Then we need the third. Now for r equals 3, so here it doesn't depend on it's valid, it is true for any x, y, z, but in particular to our point, we need only our point. So b3 now, b3 at x, y, z. So here we consider, we go up to 3, so the third derivative, we include the third derivative, so we will have this 1 1 1 and the whole SN here. So we have 0 1 1, then x, sorry, let's look what is, yes, so 0 1 and 1, yes, then here 1 1, yes, 1 and 0, and for z is 1, And finally LZ. We found for LX it's 1, 1 and 0 for that. Great. And if you compute this search determinant, you get 3, which is positive. Not minus 3, you will get minus 3, which is negative. So you need to check then. So you see here, either, so we are asked to look for maximum, but if we weren't asked, so we cannot, that means M here is 1. So if I choose the first test, I will get negative with positive, which is negative. So I'm not here. But if I keep here with R, R is 2 for the first, B for B2, so it remains positive. For R equal 3, so here B3 is negative with the minus 1 power 3 will be negative. Negative and negative gives me positive. So we will have minus 1, 3 B3. Okay, at 1, 1, 1 is 3 is positive, and minus 1, 2 B2 at 1, 1, 1 is 2 and it is positive. So from here I can say that 111 is the local maximum. Okay, so so 1, the point 111 is a local maximum point. Okay, great. So this is how you can apply the. Okay, so this is how you need to pay attention to many details. Yes, so you need to practice more so that you can see how it works. Okay. Okay.